he completed his.
Dr. Biju Kumar, thank you very much, Dr. Sunil Kumar, for the very kind introduction. It's a great honor for me to be here to present this seminar. And I also received the invitation with great honor too. Well, good evening to you all. I speak from Rio de Janeiro. This is 10:30 a.m. here. Today it's a beautiful sunny day, and the temperature right now is 23 centigrade. So before I start, let me list here and mention my collaborators in the works that I'm going to present. They are listed in here in alphabetical order. This list includes students and former students, as well as colleagues and good friends from different countries whom I have the privilege to work with. This is the summary of my presentation. I'm going to talk about the motivation for this research, which includes the solution of inverse heat transfer problems within the Bayesian framework of statistics. Then I will present some of my past and current works related to the thermal treatment of cancer, and eventually I'll come to some conclusion. As you can imagine, the main motivation for this research has been the thermal treatment of cancer, as the title of this seminar says, and the use of heat for the treatment of cancer, it can be aimed at a mild temperature increase of the tumor, in order to make their cells more susceptible to the effects of other treatments like radiotherapy or chemotherapy. Alternatively, it can also be aimed at a large temperature increase of the tumor to kill their cells solely by the effects of heat. And within the medical community, these treatments, they are usually referred to as hyperthermia and thermal ablation, respectively. Although the temperature level is not the only important factor to cause thermal damage to the tissues, thermal ablation is usually associated with temperatures above 50 centigrade, which causes cell necrosis. On the other hand, the hyperthermia, it's usually considered when the temperatures of the tumor are raised to values around 41 to 45 degrees centigrade. In this range of temperatures, heat-induced cytotoxic response is produced. And it has also been noticed an increase in the cytotoxic effects of radiation chemotherapy drugs. However, temperatures below 43 centigrades, they can induce thermal tolerance on the cells, like the action of what is called the heat shock proteins. Recent advances in nanotechnology, they have raised again the interest on the use of heat for the treatment of cancer by selectively increasing the temperature of the tumor cells containing the nanoparticles while reducing the thermal damage to the surrounding healthy cells. In fact, nanoparticles injected into the bloodstream, they tend to naturally accumulate in the tumors due to this enhanced permeability and retention effect, which result from the hypermobility of the vascular endothelial cells and also by the imperative lymphatic drainage in the tumors. After extravasation from the blood vessels, the nanoparticles, they penetrate in the tumor mainly by diffusion, and they are then taken by the cells through endocytosis. Nanoparticles, they can be functionalized to target specific cancer cells, and they can also be used as drug carriers. But nanotoxicity might be an issue when the nanoparticles are picked up by the cells of the immune system, which may promote inflammation. The nanoparticles of noble metals, they exhibit what is called the surface plasmon resonance, which increases the absorption from the external energy source at a specific wavelength, as is shown here by these figures. Therefore, the nanoparticles, they can be designed in terms of their material and also of their shape and size in order to become resonance at a particular wavelengths of interest. It's also of great motivation for me, the application of inverse analysis in problems related to the thermal treatment of cancer. And inverse heat transfer problems, they are defined as shown in this slide. They deal with the estimation of known quantities appearing in the mathematical formulation of processes in thermal sciences by using measurements of temperature, heat flux, radiation intensities, etc. So inverse problems, they are usually associated with direct measurements. So we come to the question, why inverse problems are important for the thermal treatment of cancer, and I would move a step ahead and also consider the inverse design of these thermal treatments. There are many reasons, and here I list some. First, the hyperthermal and thermoablation, they require treatment planning or even a predictive control of the temperature distribution in order to minimize damage to health cells, like any other cancer treatment. Therefore, mathematical models, they play an important role for the thermal treatment of cancer. Bioheat transfer models, they generally include many uncertain parameters. For example, the properties of tissues, they depend on the physiological state of a patient. And they also exhibit a large variability from individual to individual. As we know, the estimation of model parameters is fundamentally an inverse problem. There are some techniques for the measurement of the internal temperature during the thermal treatment, like magnetic resonance or photoacoustic. But these techniques, they are also related to the indirect measurements through the solution of inverse problems. And also, there are different bioheat transfer models available in the literature since the classical model of Penus, it was proposed in 1948. All of these models, they present some limitations in terms of the hypothesis which are assumed valid. Also, there are different models available for the thermal damage caused to the cells. There is some message here. Oh, okay. Okay. I'm going to approve. Okay. Okay, my message here. Okay. Okay. So, okay, all right. So I see now. Thank you very much. Thank you. But now I cannot move these slides here. Maybe if I close this. Okay, now I can move this. Sorry. And also related to the models, there are many models proposed for the thermal damage caused to cells or tissues. So we come to the problem of model selection and model calibration that can be used to accurately represent all the physical processes involved in the thermal treatment of cancer. Our lines along the last 10 years, they have included, oops, I'm sorry. Okay, yeah. Okay, they have included different works, mainly computational works, related to the indirect measurements of the temperature, to model selection and model calibration, to the development of nanoparticles, and this in association with a very good friend from the material science department of my university, to the analysis of the hyperthermia and chemotherapy, And more recently, our works have dealt with the design under uncertainty of the thermal trick. For the solution of the related inverse problems in these applications, we have been using techniques within the Bayesian framework of statistics. Just a remark here that, in my opinion, the most complete reference for the solution of inverse problems by using techniques within the Bayesian framework of statistics is this book by Helcio and Sommersallo. And I would like also to mention that I have been mainly working with Bayesian techniques after a visit of Jari Kaipo and Ville Kohlemann to our department in 2005, when they taught a very nice graduate course on the subject. Then really afterwards, I really changed the methodology that I have been using for the solution of the inverse problem. And for the solution of inverse problems within the Bayesian framework, we have to consider that all variables, they are random variables, and we follow these basic steps. The first step, we build based on the information that we have available for the parameters before the measurements are taken. We build what is called a prior information for the parameters, which is the probability distribution function. Okay, that collects all this, that represents all this prior information available for the parameter. Then we have to select a likelihood function that appropriately models the measurement errors. The likelihood function, it involves a relation between the observations and the mathematical model of the physical problem under analysis. And the last step is to develop methods to explore what is called the posterior density function, which is the conditional probability of the unknown parameters given the measurements. The posterior, the posterior, it's related to the prior and to the likelihood by Bayes' theorem. Actually, Bayes' theorem is attributed to the mathematical expression to Bayes' theorem is attributed to Laplace. And this density in the denominator, it's called evidence, and it plays the role of a normalizing constant. And for most applications, it's not required. Inverse problems can be solved within the Bayesian framework of statistics in different ways. For example, a maximum a posteriori estimate can be obtained if the posterior is analytical, like when we have the likelihood and conjugate to the prior. This is by solving this optimization problem, we get a pointer estimate for the parameters. But there are cases that the posterior is not analytical or numerical integrations required for the estimates, they are not practical. And in this case, we can make use of what is called Markov chain Monte Carlo methods, or MC methods. And in this case, we obtain the inference, we solve the inverse problem through the inference on the posterior probability distribution by making inference on the samples that were generated with the Markov chain Monte Carlo method. For example, here we okay. So, for example, here we have the Markov chain for one single parameter, and after the chain reaches equilibrium, we can use those samples to compute the statistics of the distribution of the posterior distribution for this parameter. On the right, we have a similar example, but now we have two parameters. So after we neglect those samples, we can compute the statistics by using the samples of the equilibrium function distribution. State estimation problems, they are also solved. State estimation problems, they are also solved with the Bayesian framework of statistics. State estimation problems, they aim at the sequential estimation of the desired dynamic state variables by using all the knowledge available about the phenomena of interest and also the measurement devices. For linear and Gaussian problems, the Kalman filter is the optimal solution. Although extensions of the Kalman filter, they have been developed for non-linear or non-Gaussian models, what appears to be the most robust and general techniques for the solution of this kind of problems are sequential Monte Carlo methods. In these methods, which are usually called particle filters, the posterior density is represented in terms of random samples and their associated weights. However, there are many situations where the likelihood is not exactly known, and they cannot be approximated in terms of analytical distribution. There might also be situations in which the calculation of the actual likelihood demands a large computational time, and thus requiring model reduction or data compression. For these situations, the approximate Bayesian computation or ABC techniques, they can be applied because they deal with the measurement or total errors that may not be appropriately modeled in terms of the analytical distribution or the computation of the analytical of the likelihood function. It can be very time consuming. Now, I would like to present some of our past and current works. In this example, a sphere that simulates a tumor inside a healthy tissue, it contains nanoparticles, and it's heated by radio frequency through electrodes located on the surface of this region. The transient temperature field in the whole region, it's recovered by solving the state estimation problem with the particle filter, and by using the measurement of one single intrusive sensor located inside the tumor. So this figure, it shows the simulated measurements as well as the exact and the estimated temperatures. And we notice that the estimated temperatures, they're in better agreement with the exact ones than the measurements as a result of the particle filter solution, which also provides the uncertainties related to the estimated temperature. And while this figure here at the bottom right, it illustrates the solution of the state estimation problem at a position inside the tumor where temperature measurements are not available, and this is also very accurate. Oops, I'm sorry. This analysis it has also been extended for the radio frequency heating of a tumor in a more realistic geometry that involves different organs in the abdomen, and the tumor is located inside the pancreas, and this is the results obtained for a point where the measurements are not available inside the pancreas. Okay, now we apply the same techniques to a similar problem, but involving a skin cancer, which is heated by a laser beam. This is the exact and the recovered temperatures along this line here, where the tumor is located here in the region where the temperatures are higher, and these are these figures. They present the exact and the estimated temperatures in the whole region at two different times, and these estimates, they were obtained with 100 particles, and this one here with 250 particles, and we can see that the estimates are quite accurate, especially in the region of the tumor where the temperatures are higher. These techniques, this technique, it has been validated with phantoms heated by a laser, and this phantom contained a region that mimics the tumor, and in this region, in the format of a disk, it contains iron oxide nanoparticles that we have manufactured. The internal temperatures, they were monitored by thermocouples. We can see the wires of the thermocouples here. And the surface temperature, it was monitored by an infrared camera, and this whole region was heated by a laser. We can see here a picture taken during the laser heating, the picture taken by the infrared camera. The state estimation problem, in this case, it was solved with the measurements of one single thermocouple inside the medium, while the measurements of the other thermocouples and also from the infrared camera, they were simply used as a validation for the validation of the estimation procedure. In this figure, we show the measurements used for the solution of the state estimation problem, as well as the estimated temperatures in this region, and they are in very good agreement. But in this figure on the right, we show that the agreement between the measurements and the estimated temperatures at the surface of the phantom, they are also in very good agreement. This is the radial variation at a specific time. And the point here is that only those measurements, they were used for the solution of the Mercy problem, and these ones, they were only used for validation. These two previous examples of indirect measurements of the temperature, by the solution of a state estimation problem, they involve the measurements of one single intrusive temperature sensor. I would like now to present two cases involving non-intrusive measurements, but these measurements, they are provided by other physics. This first example, the measurements, they are provided by magnetic resonance. It has been shown that the local temperature variation, it's related to the variation of the phase shift delta phi by this linear expression. Although the direct inversion of this equation, it provides measurements of the temperature, internal temperature variation, we have shown that the solution of related state estimation problems reduces the measurement uncertainties. In this case, this equation is used as an observation model, which is coupled to an evolution bioheat transfer model. This approach, it allows for the estimation of the temperature itself, in addition to the temperature variation as well. And we have applied this technique to this irregular region containing different tissues and a tumor. Okay. So the solution of the state estimation problem, it also allows that the measurements be taken in a region around the tumor, but the temperatures be estimated in the whole region and even in a more refined mesh, like we have considered here. Okay. So this is the, this is the exact temperature variation simulated, and these are the estimated temperature variations obtained with the Kalman filter by solving the state estimation problem and considering only measurements taken in this region around the tumor. So we can see that the estimations are quite accurate. Now, I'd like to show you some results obtained with another non-intrusive indirect temperature measurement by using photoacoustic thermometry. Photoacoustic imaging, it relies on the generation of pressure waves inside the tissues which result from the absorption of the energy of a laser pulse. The amplitudes of the acoustic waves, they are proportional to the tissue's scattering and absorption coefficients in the laser wavelength. And they also depend on the Grunas's parameter, which includes the local sound velocity, thermal expansion coefficient, and the specific heat. The temperature dependence of these physical properties, they directly affect the amplitude of the generated acoustic waves. As a result, photoacoustic pressure measurements, they have been used for the indirect measurement of temperature in biological tissues and water solution. Such as for the magnetic resonance thermometry, photoacoustic temperature measurements, they can be obtained by direct inversion of a very simple equation. But the solution of an inverse problem can reduce the measurement themselves. In this case, we solved an inverse problem to recover the spatial variation of the Grunas's parameter, which has been shown to be a linear function of the temperature. We have considered the case of a skin cancer in a rectangular region, which is heated by a laser. And this tumor, it contains nanoparticles, and a laser pulse is used to generate the acoustic pulses, which are measured by the non-intrusive transducer. The photoacoustic thermometry inverse problem, it was solved by the Markov chain Monte Carlo method, where you can see this is the exact temperatures, and these are the estimated temperatures, and they are in very good agreement, even on a coarse mesh. And it has also been solved with the Kalman filter for the sequential estimation of the transient temperature in the whole region, as shown here. And we notice in these figures that the effects of the non-uniform distribution of the nanoparticles inside the tumor, which were simulated in this case, they could be quite well recovered. And this non-uniform distribution of the nanoparticles, it resulted on the non-uniform heating of the tumor. Although not related to cancer treatment, we also solved the inverse photoacoustic thermometry problem as an auxiliary tool for the diagnosis of inflammatory bowel diseases. In this case, both the laser and the acoustic transducer, they are located at the tip of a shaft that rotates inside a catheter here in the which is inserted in the bowel lumen. And the simulated inflamed regions, they could be quite well recovered by the inverse analysis as shown here on the right. Now moving to another subject, which involves the thermal ablation and the removal of tissue by laser heating. A numerical model was implemented and the direct problem was solved, but a comparison of the results obtained in this work with the experimental data available in the literature for the ablation of rat liver reveals an excellent agreement for the crater position and shape. Unfortunately, these were not we could not get a good agreement of the thermal damage models. Actually, we examined 3 different models in this case, with the regions of coagulation and necrosis for the same experiment. So this model 1 and model 2, they were the Arrhenius thermal damage model with different parameters, and the model 3 was the two-state model of Feng et al. So we applied this algorithm of Tony et al. For the simultaneous model selection and model calibration, but in this case, we have used simulated measurements. The simulated measurements, they were generated with the Arrhenius model, model 1, and both the Arrhenius model and the two-state model, they competed here in the first iteration of this algorithm. But we can see that eventually only the correct model was selected from iteration 8 onwards. But some iterations, they were required for the correct model calibration. The algorithm of Ton et al., it was then used with actual experimental data to calibrate the parameters of an Arrhenius thermal damage model, and by using an ex vivo tissue here that was heated by radiation. And so the temperature measurements were used in the verse analysis. The temperature measurements were obtained with the infrared. Okay, so besides the iron oxide nanoparticles that were used in the experiments with the phantons presented before, our group, in collaboration with the material science department, we have also developed other nanoparticles with possible application in cancer thermal treatments. The focus here was the synthesis of nanostructure palladium and palladium ceria and their respective hydrides. The use of hydrogen is very promising for the thermal cancer therapy due to its important role in physiological regulation, besides exhibiting good biomedical applicability and biosafety. Hydrogen is a therapeutic antioxidant that can selectively reduce the hydroxyl radical. For the thermal treatment, hydrogen must be safely and effectively stored in nanoparticles to target specific cancer cells and also to allow its controlled release. Then why palladium? And because nanoparticles of palladium hydride, they can store large amounts of hydrogen, and they exhibit good biocompatibility, as well as high photothermal conversion efficiency in the near infrared range. And so why we say this, because these are the figures with the palladium nanocubes. The mean size of those nanocubes were about 20 nanometers. And we made some experiments with nanofluids produced with those nanoparticles, also through laser heating, and by measuring the surface temperature of the nanofluids with the infrared camera. This is 96 well plate that also contains distilled water in some of the wells, and these measurements here, they were used only for control, and this is the figure of the heated nanofluid inside of one of the wells. Okay? This figure, it shows the temperature variation at the center points of the surface of the nanofluids. For two different concentrations, they were only palladium nanocubes nanofluids, and this is was also for a constant power of the laser. We can see that the effect of the hydrogen in the nanoparticles was remarkable. With the palladium nanofluids, palladium nanocubes that were hydrogenated, the temperature increased here reached 32 centigrades. While the common nanofluids with the common palladium nanocubes, not their hydrogenated versions, it reached 25 centigrades. And for a comparison, we have this red line here, which shows the temperature increase of the distilled water when it was heated, which was less than 1 degree centigrade. So we also applied the Metropolis-Hastings algorithm to estimate model parameters of those heated nanofluids. We considered a model that included natural convection effects, because the largest source term it occurs here in the region below the laser beam, around the cylinder's center line. So this source term, it decreases for deep regions below the top surface due to the absorption of the laser beam by the nanofluid. It also decreases radially, and this heat source, it induces a single natural convection cell. So the nanofluid, it moves upwards here in the central region with larger temperatures, and downwards near the lateral surface of the well, and where the temperatures here are smaller. So the temperature gradients actually inside the well, they happen to be quite large. So these are the samples obtained with MCMC for the absorption coefficient, but also for the external heat transfer coefficient. And we can see that the estimated temperatures obtained with these parameters and the measurements, they are actually in very good agreement. So that both the model and the estimated parameters, they appropriately represent the physics of the problem. Our objective now in this work is to examine the coupled hyperthermia and chemotherapy effects during in vitro diode laser heating of a culture of cells containing nanoparticles. The Monte Carlo parameter estimation direct simulation has already been developed for a simulated experiment that followed a protocol similar to that used by Tang and McGoran. But for this combined Monte Carlo direct simulation inverse analysis framework, we have simulated the behavior of prostate cancer cells under the effects of doxorubicin. And the choice for this cell line and for this chemotherapy drug was due to our experience in the past with model selection and calibration of the in vitro chemotherapy experiment, as I show in this region, in this figure here, which illustrates the application of Tony et al.'s algorithm of approximating Bayesian population. Well, so some of our recent works, they have focused on the design and the uncertainty for an individualized thermal treatment. In this example, the design of the thermal ablation of a tumor by heating imposed with high-intensity focused ultrasound, it was performed in a probabilistic sense. So uncertainties in the model parameters and in the design variables, they were modeled by the prior distribution, while the likelihood, it represented the desired outcomes and their acceptable uncertainties. So for this example, the simulations were performed in a rectangular domain containing water in different tissues and a rectangular tumor. And the high flow transducer, it's here located in the water. Samples of the posterior distribution, they were obtained with this Metropolis-Hastings algorithm with sampling by blocks of parameters. The two blocks of parameters contained the physical properties and the design variable. So this figure illustrates our objective here, the likelihood represented the desired probability of dead cells and the standard deviations of these Gaussian likelihood We show that our objective here is a high probability of dead cells in the tumor region and a small probability of cells in the region containing the health cells, but we allow for a transition between these two regions, the tumor and the health cells regions. Okay? The results for the optimal design are shown in these figures. These figures show that the optimally designed hitting time and also the high focal point, they provide a mean dead cell probability around 90 to 90% inside the tumor. And at the same time that such probability was almost zero far from the tumor. On the other hand, we noticed that some parts of the tumor did not reach the desired probability of dead cells. So other design variables must also be considered in future ones. Before I finish, let me mention that some recent experimental results of McGoran, they have revealed that the diffusion of the nanoparticles into spheroids, they increase with temperature. Spheroids, they are three-dimensional cell aggregations that they can mimic the structural character of microtumors. A fluorescence technique was used in to indirectly measure the concentration of the nanoparticles in the spheroid. So this figure here on the top, it shows that the nanoparticles, they were more concentrated in the periphery of the spheroid when the incubation temperature was 37 centigrades. On the other hand, the fluorescence was more diffuse. The nanoparticles penetrated deeper into the spheroid when it was incubated at 43 centigrades, as shown by this figure. Some conclusions now. I'm almost finishing. These Bayesian techniques, they were accurate and robust for the solution of inverse problems related to the thermal treatment of cancer. They have also been used for the optimal design under uncertainties of the hyperthermic treatment of cancer. In particular, we have used this Metropolis Hastings algorithm with design by block, with sampling, by block of parameters. And let me move to this slide, which I think that is more interesting, because this is, I think that, in my opinion, it has to be done. At least we have to test these computational algorithms with more realistic test cases involving three-dimensional geometries of multiple organs. Also, we need to apply those inverse techniques to actual experimental data, particularly at the cell and tissue, and by tissue I also mentioned spheroid scale. Some questions that need to be answered. For example, how individual cells and spheroids containing nanoparticles, they behave when they are heated by laser or sources. Also, what are the local effects of these nanoparticles in cells and the spheroids? The temperature variations of nanofluids containing palladium nanotubes or palladium serine nanoparticles, they were substantially larger than that of distilled water, demonstrating the photothermal effect of these nanoparticles, in particular those that were hydrogenated. But can these nanoparticles be actually used as hydrogen or drug carriers to tumors? We have to work on this. So finally, I would like to acknowledge the Indian Society of Heat and Mass Transfer London chapter for the invitation, in particular Dr. Sunil Kumar and Dr. Biju Kumar. Thank you very much. It's a great honor to be here. I would like also to acknowledge the support provided by agencies of the Brazilian government. And I guess this is it. Thank you.